Mr. William, last week we saw that acyl chlorides, are they your usual electrophiles?
No, we learned last week that acyl chlorides, they are super reactive, right? So I think we have a name to describe them, right?
Yeah, we do.
What do we call them?
We call them super
electrophile. Okay guys, so today what we're going to do is we're going to compare the reactivity across all the different halogenal compounds, right? What have we learned so far? We have learned acyl chlorides, we have learned alkyl chlorides, we have also learned aryl chlorides. Now we're going to look at how hydrolysis actually happens, right? What is hydrolysis? Right, hydrolysis means you're going to attack an electrophile either by using water or OH minus. Now, Mr. Tim, can you remind us what makes water and OH minus a nucleophile?
Well, they both have that lone pair on the oxygen, right?
Right, so this guy has a lone pair and OH minus, yes, there's a lone pair, but there's an additional negative charge on them. So in terms of the strength of a nucleophile, which one is stronger?
The moment you see a negative charge, OH minus is now a stronger nucleophile than H2O. Okay.
All right, let's write this down together. This is going to be a stronger nucleophile. All right, so in this case, if you're going to do a hydrolysis with either a weak nucleophile or strong nucleophile, what it means is the compound which is the most reactive or the most electrophilic will be the easiest to do nucleophilic substitution. Right, so let's break it down, the sequence of reactivity. Now when we look at acyl chloride, as we term them as a super electrophile, it means that they are the most reactive. And in terms of the conditions, do we expect the harshest condition or the mildest condition?
Super mild, because it's so reactive, right?
All right, let's write this down. If you're super electrophile, you're going to require the mildest conditions to do a reaction. Now, if you compare acyl chloride with alkyl chloride, now, Mr. Tim, can you just bring us through, right? What is the difference in terms of the delta plus?
Well, the acyl chloride has a much bigger delta plus because the carbon is bonded to two very electronegative atoms. But in the halogenate alkene, it's only bonded to one electronegative atom, right? So smaller delta plus.
Right. So if it's a smaller delta plus, it will also mean that it is less electrophilic and less reactive. Maybe we have a term, since we call this a super electrophile, we'll just call alkyl chloride a normal electrophile, right? Maybe we'll just use this. Okay, this is a normal electrophile. And the last one, what you see here is an aryl chloride. Now, what is that special thing every time we mention an aryl chloride?
Partial double bond.
Yes, all right, because of the orbital overlap, that's why they have partial double bond character. And do we expect them to react?
No way. If a nucleophile tries to come in, it repels, right?
So we will call this, right, for comparison purpose, we'll call this a non-electrophile.
Okay.
All right. So you can see a super electrophile requires the mildest condition, and a non-electrophile probably will have no reaction, while a normal electrophile is probably going to require a harsher condition for this to work, right? So we're going to frame it this way in terms of the reactivity, right? And Mr. Tim, can you bring us through, right? How then will they react with water?
Of course, let's go, all right? Now, first things first, acyl chlorides, the super electrophile, so you'll be able to undergo a reaction with your nucleophilic water molecule. So I'm going to clean this up first. Now, tell yourself this, right? If I bring a water molecule here, and remind yourself, water nucleophile, is that a strong or weak nucleophile?
It's a very weak nucleophile because they only have lone pairs and therefore they have only delta minus.
So no negative charge, right? Just a partial negative. Expose the lone pair with me, attack that super electrophile, break that CCl bond, okay? So because acyl chlorides are so electron deficient, okay, it is able to react with the weak nucleophile water molecule and you'll be able to hydrolyze it, all right? To give you this, if you guys can remember, we saw this just now, your carboxylic acid functional group, all right? Now, Mr. William, before we move on, I want you to think about this as well, okay? If your acyl chloride can react with such a weak nucleophile, like water, do you think it can react with OH minus?
Definitely.
Definitely, okay? So guys, don't just memorize this like a dum-dum.
Emotional, damn it!
You need to understand it, okay? Now, Mr. William, bring me through alkyl halides. Let's go.
All right, so the difference between alkyl halide and acyl chloride is the fact that alkyl chloride, they are more electrophilic, so we just use the term a normal electrophile, right? So a normal electrophile, you expect slightly harsher conditions.
Of course.
Right, so the difference now is you require something that's charged, right? So you require OH minus. So recall several reactions we have learned before. The key thing, right, is you require a strong nucleophile. You also require harsher conditions. You must have heating before the reaction works. And in an event, you're working with different types of alkyl halides. Do remember the difference between CF all the way to CI. The key factor will be the bond energy and the bond strength. So do remember, CF bonds, they are way too strong. You're not able to do any sort of cleavage on the CF bonds. So generally, alkyl fluorides, they are not reactive. But if you look at Ci, these are the weakest bond, and therefore it will be the easiest to break, and that's why reaction will go the fastest. But the key thing is you're going to require someone that's charged in order to react with an alkyl chloride. All right, now what about aryl chlorides, Mr. Tim?
Let's finish this off. Now guys, we saw this in hydroxyl compounds as well, okay? So I hope, or halogenate alkanes, excuse me. So I hope you guys can still remember. So I'm going to draw for you right now an aryl chloride, okay? So aryl, a benzene ring, directly attached to a chlorine, okay? Now there are two reasons for why aryl chlorides do not undergo hydrolysis with OH minus or water, because here's the thing. Now Mr. William, remind me, right? If a nucleophile tries to come in to attack this carbon here, can I say that this carbon is electrophilic?
It's not exactly electrophilic.
No, right?
No.
Because this carbon is part of your benzene ring, and you know that your benzene ring has how many pi electrons?
And 6 pi electrons?
Yeah, so that brown carbon there, it is part of the benzene ring. It is not that electron poor. It's actually electron rich. So if the nucleophile tries to come in to attack this carbon, there is no way. It will definitely repel, okay? And that's exactly what we see here. Reason number one, the carbon, electron rich, repels nucleophiles away. Now the other reason is the more important one, and we have said this before, that three special words, partial double bond. So again, Mr. Willem, remind me, the lone pair on the chlorine there, what orbital is it found in?
It's found in the p orbital.
Yeah, so once again, these two p orbitals here, I'm going to highlight this with you. They are parallel, okay, and they are adjacent to each other. So again, they are going to sideways overlap, and I'm going to dot, 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 dot. You tell yourself here, what we have here is a partial double bond character. So the nucleophile, even if the nucleophile tries to come in to attack this carbon, that CCl bond will never break, okay? And that's why aryl chlorides do not undergo hydrolysis at any conditions, okay?
Now, I think all this is important theory to know, but where is the application is really what we call the distinguishing test, right? In an event, you have these three compounds present. How do I know which one is what? So the usual way for us to do this, as you can see below, is to use either aqueous or ethanolic silver nitrate. Now, when we look at ethanolic silver nitrate, I think the first few things that will cross students' mind is they will focus on the Ag+. And usually, what does this Ag+ do?
Well, it's going to cause precipitation, right?
So you're going to react with an X-, and you're going to form precipitates of silver halide. So I think most students are able to recognize this, but they're not able to recognize that you are also throwing in either aqueous or ethanolic, right? So in an event, it is aqueous. You know, aqueous contains water, and therefore water is going to behave as a
nucleophile, right?
Right, this is a nucleophile, right? Alternatively, you could also be using ethanol. Ethanol, for the same reason, the oxygen has a lone pair, they will be a nucleophile as well. So guys, we need you to realize, right, and when you add in ethanolic or aqueous silver nitrate, you're adding two things. Number one, you're adding in the nucleophile, and number two, you're adding in the Ag+ for precipitation at the same time, right? So let's bring this across to an acyl chloride, right? So you can see, if I give you a RCOCl, what is going to happen is, let's assume we're going to use aqueous. Okay, let's assume it's aqueous. So what will happen initially is your acyl chloride is going to react with water, the reaction we have learned previously. Now you're going to form carboxylic acid, and you're going to form HCl. But bear in mind, this is in aqueous medium, so the HCl will still be dissolved in the solution. You're going to have Cl- floating around, and at the same time, your Ag+ will instantly precipitate out the Cl-, and you're going to see a white precipitate of AgCl instantly, right? So guys, in terms of reaction, bear in mind, two things are happening. Number one, the nucleophilic attack, and number two, the precipitation. So that's why you can see the white precipitate of AgCl is observed immediately, right? Immediately, without any sort of heating, right? But if you work on alkyl chloride, you don't expect any sort of immediate precipitate, but after prolonged heating, some of the chlorides, they will break away. You will then be able to see the precipitate of AgCl. Okay, and in the case of your aryl halide, then what happens? Partial double bond. I think this is like the many times we have talked about this. So once you have a partial double bond character, it is unbreakable. You're not going to see any sort of precipitate. Right? So guys, do take note. Write this down for yourself. This is a distinguishing test. Right? And that's what this whole page is really all about.
Alright class, we're going to be talking about esters now. And you guys have seen this also in Sec 4. Esters, they're very sweet smelling, right? They're found in your fruits, they're found in perfumes. But William, are all esters really that sweet smelling?
Well, talking about esters, I used to have this crush on this girl called Esther. You know, when I think about her, it just reminds me of strawberries.
Okay guys, so what we have here is carboxylic acids versus esters, right? Small things first, just tell yourself, the main difference is that in a carboxylic acid, you have this OH functional group bonded to your acyl group, that's a carboxylic acid. Now for an ester, it is not an OH, it is an OR. The R is just an alkyl group, okay? So we have it here. Main difference between carboxylic acids and esters is that carboxylic acids, of course, they are acidic, okay? But esters, they're actually neutral, all right? Now I'm going to run you through how to name esters, okay? So listen up. But before that, I have to teach you how to form esters first, okay? We have seen this before, right? In the earlier video, in the earlier lesson. We have a carboxylic acid here. It's going to react with an alcohol, okay? Remind yourself, what we're going to do is circle that OH from the carboxylic acid, circle the H from the alcohol. You're going to remove that water molecule. Look at this. I'm going to pluck this out. Look. Okay, I'm going to put that there. That's water. I'm going to take this. I'm going to combine, all right? Now you tell yourself this, highlight this with me. Carbon, COO, that's your ester functional group. Now how do we name it? Now we always look at ester in two parts, right? Now the part on the left, that is your carboxylic acid part, okay? And the part on the right is your alcohol part. So that's how we name. First things first, do this with me. Always see in two parts. So cut, 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 all right? Now Mr. William, help me out. On the left-hand side here, this is a carboxylic acid portion. Now, how many carbons do you see?
We have 2 carbons.
We have 2 carbons. Now, but we don't call this ethanoic acid, we call this ethanoate. So we put the acid naming at the back, and we put the alcohol naming in the front. Now, in this alcohol part, you guys see 2 carbons. So it's ethanol, but again, we don't call it ethanol, we call it ethyl. So it becomes ethyl ethanoate, okay? Once more, Mr. Willem, tell me, on this left-hand side, how many carbons do I have?
I see 2 carbons.
Again, 2 ethanoate. We put the acid naming at the back. Now, what about the right-hand side, Mr. William?
It looks like a benzene,
Okay.
but a benzene we typically call a phenol group.
So instead of phenol, we call it now phenol, right? So this becomes alcohol in front, phenol, ethanoate. Last but not least, let's wrap things up. On the left-hand side, again, I see something like a benzoic acid, right? But instead of benzoic, we call it benzoate. And on the right-hand side here, I see a phenol, but instead of phenol, again, I call it phenol. Okay? Now, Mr. Willem, could you help us with question 27?
Yeah, of course. Right, so as Mr. Tim is telling us, the key thing is to break down carboxylic acid into 2 parts. Now, one of the little things that may just help you that little bit is to actually do some sort of numbering. Okay, so for example, we will say this is the first thing to name, the alkyl group, right? And this is the second thing that we will name, which is the carboxylic acid portion, right? So over here, we're going to work through this question, right? As you can see, we're going to break it up over here. And the first thing to name is always the alkyl group on the oxygen, right? So we're going to put a number 1 over here. And then number 2 is to name the carboxylic acid portion. All right, so we can see this is like a methanol, right? It came from the methanol. So we're going to call this methyl. And on the right-hand side, now what is the name if it's a carboxylic acid, Mr. Tim?
Now, I see 4 carbons. 4 carbons is so butanoic acid, but we call it butanoate.
That's right. Instead of calling it butanoic acid, just change the name a little bit, and we call this a butanoate. All right, so number 1 and number 2. Just be mindful because very often students may mix up the sequence, and once they mix up the sequence, then you're going to lose a lot of marks for sure. All right. Okay, now this question is a bit different because you're given the name and you have to draw the structure, right? So the first thing to do is to perhaps get the skeleton out. You will see that this is your C double bond O with the oxygen, right? Now on one side you have your metanoate, right? So metanoate will be a 1 carbon carboxylic acid. It came from metanoic acid. right? So this is how it looks like, because the original backbone is going to be like this, COOH with just one hydrogen, right? So you can imagine this is going to change into the metanoate portion. And the left-hand side, this is coming from the propyl group. So I'm going to label here number 1, and you expect 3 carbons. And that's it, your propyl metanoate. Okay, all right, now the last one, we're going to chop this off here. Now, as a team, what do we call this portion? We should call this first, rather. Okay, let me just clean this up. This is the first one that we call, and we'll call this?
Again, I see a 1 carbon alcohol, so I call it a methyl.
Okay, very good. This is a methyl. And then on the left-hand side, this is the second thing that we will name. And this time round, you see the backbone that comes from?
I see a benzene ring connected to a C double bond O, so probably came from benzoic acid. So we call this benzoate.
Yep,
right?
we're just going to change a little bit, and we call this a methyl benzoate.
Perfect, that's it.
That's it, right, the naming process. Now, why don't you walk us through some of the reactions? I think we have seen this many times, as we say, there's a lot of reactions that's integrated together. Come, let's remind the class, Mr. Team.
Okay, so I'll be very brief here, right? So again, you just tell yourself, how do you prepare an ester? You take an alcohol, right, OH functional group, and you're going to react it with the carboxylic acid functional group. One last time, go to the carboxylic acid, circle that OH, go to the alcohol, circle the H, remove them, and that's how you get water, okay? So you take this oxygen here, and you connect it to this carbon here in brown. And that is how you get your ester functional group. Now take note, since we are looking at carboxylic acids, this reaction is actually reversible, okay? So we have said this before, Mr. William ran us through very quickly. If I want to increase the yield of my reaction, because it's reversible, I need to remove the water molecule. So my Le Chatelier's principle can push my POE to the right. So therefore, what kind of reagent do I need to use?
Any dehydrating agent, and that's where corn H2SO4 comes in.
Perfect, and that's where corn H2SO4, we see that there, okay? Now, look at acyl chlorides. So acyl chloride, remind us again, Ms. William, they are your super electrophiles, right? Yes. So because they are super electrophiles, this reaction is no longer reversible. It is now a full arrow, okay? So tell yourself again, similar things, but instead of going to the carboxylic acid now, we're going to go to the acyl chloride, circle the Cl, or used to be OH, right? Now we're going to circle the Cl, circle the H from the alcohol, get rid of them, bye-bye, tell yourself, HCl now, instead of water. Once again, go to the oxygen here, connect it to that carbon, and here you get your ester functional group. Now last thing to take note of, because the acyl chlorides, they are super electrophiles, take note again, room temperature and pressure, irreversible reaction, all right?
Yeah, I think the key thing to realize is there are 2 ways for you to form esters. All right, so the first reaction is to use carboxylic acid, and the second is acyl chloride. Now, typically, we'll prefer the second reaction,
for sure,
right? For a clear reason that this is going to be a much higher yield, and also the fact that you're going to require milder conditions for this reaction to work. Right, always remember, acyl chlorides, they're super electrophile. So the reaction is going to go fast and furious, and the yield is going to be really high. All right, now something related is reaction 8.7. Now 8.7 is also the formation of an ester, but this ester is coming from the phenol backbone instead of the alcohol backbone. Now do realize that the difference between phenols and alcohol, now maybe let's run through mechanistically so that they have a good understanding, right, Mr. Tim?
Yeah.
Now we understand in order for the reaction to work, what you require is we require the lone pair from the oxygen to attack the delta plus carbon and kick the living group away. All right. So how well this guy reacts largely depends on the nucleophilicity, right? So shall we comment what is the difference in the availability of the lone pair for phenol against that of alcohol?
Well, so here's the thing. So if you look at this R group here in the alcohol, R groups are electron, Mr. William? Donating. So we're going to donate electrons to the oxygen there. So the lone pair is actually activated, right?
It's more powerful, right?
Yeah, super powerful. So again, you compare this, right, guys, with a phenol. Now this lone pair here, again, notice how it is connected directly to a pi system, and I've drawn this like a billion times, okay? Now, Mr. William, remind me, right, this lone pair is also found in a
p orbital.
Okay, so again, this p orbital that a lone pair is found in, they are number 1, adjacent, number 2, they are parallel to each other. So again, they will sideway overlap, this lone pair is now sucked into the benzene ring, delocalized inside. Do you think it's available, Mr. Willem?
It'll be less available.
Yes. So phenols are actually less nucleophilic than alcohols. Okay?
Okay, so we're going to write this down. Phenols, they are generally less nucleophilic. So to compensate for the fact that they are less nucleophilic, you have to be careful of the choice of your electrophile, which is why, in this case, only the super electrophile will work. All right, so we need you to really have a deep appreciation why the reagents and conditions are different, why alcohols can have two different reagents because they are more powerful. But in the case of acyl chloride, they are less powerful, so they will only work with the super electrophile.
Okay, so guys, once again, we have an ester now. So once again, let's think, right? Are esters nucleophiles or electrophiles? Okay, so we have seen this in carboxylic acids, we have seen this in acyl chlorides. So yet again, we have another acid derivative. Focus on the carbon with me, and it's bonded to not just one, but two electronegative oxygen atoms. So again, they will suck electrons away from the carbon, making the carbon electron poor. So Mr. Willem, electrophiles or nucleophiles?
They'll be electrophiles because they bear delta plus.
Exactly, right? So once again, esters, they are electrophiles, and as usual, they will undergo nucleophilic reactions, okay? So very quickly, let's wrap this up. You draw a nucleophile here with me, nucleophile, attack the carbon here. We're going to break off that CO bond. That's it, okay? So this is called nucleophilic substitution, where the nucleophile will just sub away the OR, but this substitution takes place on this acyl C double bond O functional group, okay? Now, the reactions we'll finish in class, and that's it for today, okay?
Take care.
Take care. Bye-bye.